Okay, we have our final presenter. We have Emma Shapiro, who's a PhD student at Northwestern University.
Can you hear me now? Okay, great. Okay, well, thank you guys for staying till the last presentation. Yeah, how do we get that off? This is actually my last presentation as a PhD student, so it's bittersweet. Is that not it? What if we do this? So we should be good. Yeah, okay, perfect. So today I'm going to be presenting on a pilot scale test of a cyclodextrin-based sorbent for removing PFAS and other trace organic contaminants from municipal wastewater. So I think we've talked a little bit about this, but the inability to remove PFAS and other contaminants is a major challenge for wastewater treatment. So you can see here that PFAS enters wastewater treatment plants at variable loadings depending on location, and then it goes through the typical wastewater treatment process and then typically either exits in the biosolids and then is used in land applications, or it exits through the effluent and it's discharged back into the environment, used in groundwater recharge or in surface waters. So these contaminated discharges expose humans and ecosystems to environmental risk. This is also an issue for utilities as it poses regulatory risk and potential litigation for those facilities, especially as increasingly stringent regulations and health advisories are arising. Additionally, chemical contamination of effluent inhibits potable water reuse. Potable water reuse poses a lot of potential benefits, including ecological restoration, economic benefits, infrastructure resilience, and a range of other things. So we're not currently doing a lot of water reuse in the US. There's a bit in states like California that are a little bit more water scarce, but the global water reuse market is projected to grow about 58% over the next 5 years, which makes this critical. So how do we remove these contaminants from wastewater? So adsorption is the most promising method for removing organic contaminants from aqueous systems. That's because there are high removal rates. They can be easily incorporated into existing infrastructure that doesn't already have tertiary treatment. It's straightforward, low energy demanding, and also compatible with destruction methods. So the commercial adsorbents that you might be familiar with are activated carbons, which are macroporous resins that remove contaminants by hydrophobic interactions. These are irregularly shaped. And then you also have ion exchange resins, which are spherical, are macroporous, and they remove contaminants by electrostatics, so charged interactions. However, these existing sorbents are limited. Activated carbons have slow kinetics, they're non-selective, they're prone to clogging, and disposal can be costly. And then ion exchange, on the other hand, has limited removal of nonpolar compounds. They're expensive, they foul easily, and the best performing resins are not regenerable. And all of these limitations are heightened in wastewater. So I didn't talk about the toxicity and environmental persistence of PFAS, but I think we're all pretty familiar. That, coupled with the limitations of wastewater treatment processes and these commercial sorbents, underscore a need to develop scalable, cost-effective, next-generation materials. So cyclodextrins, these are macrocyclic oligosaccharides with 6 to 8 glucose units, so basically cyclic sugar structures, are are used commonly to overcome these limitations of conventional adsorbents. That's because these are low cost, can be made very simply, and they have high removal efficiencies for organic contaminants. And that's because they have unique structural properties. They're both hydrophilic and hydrophobic. So if you're familiar with the PFAS structure, you know it's both hydrophobic and hydrophilic. So it can remove contaminants from both ends. It also, because it has that cyclic structure, it has this interior hydrophobic cavity that can have contaminants dock inside of it. So here you can see that cyclodextrin has a specifically strong interaction with PFOA. And because it has multiple modes of removal, it's less prone to inhibition by background constituents, which you might find in wastewater. So the Dichtel group at Northwestern in the chemistry department, specifically Dr. Ziwei Lin, worked to develop cationic styrene-functionalized beta-cyclodextrin polymers, which we call StyDex because that's a long name otherwise. And these have both selective and effective contaminant removal, specifically for PFAS, but also for other organic contaminants. And that's because of the cyclodextrin in that cyclodextrin cavity, but they also were able to incorporate positive surface charges to facilitate electrostatic interactions with the PFAS. This new StyDex that was made in 2023 also has higher styrene incorporation, so higher hydrophobicity. And then this method is compatible with a variety of different polymerization methods. So it's very tunable and versatile and relatively inexpensive. So what you're left with is a material that can remove contaminants by hydrophobic interactions with the PFAS tail, as well as electrostatics with the PFAS charged head group, and then size-selective host-guest complexes within that cavity. So these were originally made as powders. Most sorbents that you find in the lab are typically made as powders. We actually then converted these powders into a bead that maintains the same absorption mechanisms, capacity, and kinetics. I'm not going to go into the process of development, but if you're interested in it, I've put that down here. But we saw that these beads that we developed were uniformly spherical across bead sizes. So we did this using a suspension polymerization approach. So we knew that they weren't just breaking apart in solution, they were relatively durable. We also looked at the BET, so the surface area, total surface area of different particle sizes, and saw that regardless of size, they had pretty similar porosities, suggesting that they had extremely high internal porosities that were the largest contributor to surface area. And then just to put this into perspective versus an activated carbon or an ion exchange, it kind of falls in the same range as the porosity of an activated carbon, more porous than an ion exchange, and then less dense than both of those. I need to go faster, actually. So these beads were tested against activated carbon and ion exchange resin. And what you can see here is that they outperform both of these in taking up the PFAS compounds, the PFAS that we were looking at, as well as the two pharmaceuticals that we were studying, except for ion exchange resin had a little bit better removal of PFBA in wastewater because of all the electrostatic interactions. But you can see with the blue, activated carbon has really low removal of PFAS in wastewater, so it's about less than 20% removal across compounds. So then today what I wanted to talk a little bit about was my pilot testing. So we did batch testing to validate these materials. We did small scale column testing to figure out the right operation conditions and screen different formulations of beads, look at different contaminants. But then we moved to pilot testing. And this was done at the O'Brien Water Reclamation Plant in Skokie. This is one of the MWRD plants, the second largest, where there's primary, secondary, and tertiary UV treatment. And this was my pilot design. We had pipes carrying in secondary treated influent into a greenhouse. Then I equipped it with 5 and 10 micron sediment filters. We had a 200-gallon tank, which we then spiked with contaminants at 500 nanogram per liter. So those were those 6 contaminants that I showed before. We packed columns with our StyDex beads and then pumped the water through those and then collected effluent samples over about 3 to 4 months. So these were operated for exactly 117 days, and we saw that individual contaminant removal varied by operation contact time. So overall, we were seeing the best removal of PFOA, PFHXS. I think that's what we all typically see. And then pretty low removals for PFBA because, as we're familiar with, that's a really challenging and mobile PFAS. And then looking at the cumulative removal across contact times, we were getting about 0.5, 0.6 micromoles per gram of total removal, which stacks up to commercial adsorbents. Then we also looked at regeneration. So we took that spent column and did in situ regeneration with 70% IPA and 20 micromolar ammonium acetate. So what that does is you have the alcohol that disrupts the hydrophobic interactions, and then you have the ammonium acetate, which screens the electrostatic forces in order for the PFAS to fall off of the sorbent. And we saw that the regeneration was really efficient, but could have been quicker. So this was about 175 bed volumes for full regeneration. The goal for a commercial resin would probably be about 10 bed volumes, so a little bit of room to grow there. This wasn't done with any sort of backwashing, so there's next steps would be optimization of that. And then we did a mass balance, and we saw that the beads had really high desorption efficiency, specifically for the PFAS. And then a little bit lower for one of the pharmaceuticals. And then the PFBA looks negative, but we had a lot of desorption during the test, so it's hard to measure for PFBA. And then we also saw that the regeneration returned the bead surface back to what it looked like before use. So here at the top, you can see a virgin bead before use. The second one is after we used it at the pilot. There's a lot of gunk on the surface, organics, fouling, and biofilm growth. And then after the regeneration, it's mostly returned to normal. And then we were able to reuse that. I don't have any reuse slides here, but we were able to reuse those. But we only did it over a single cycle. Future work would be over multiple, but not for me to do. Someone else will do that. And then lastly, this is actually operating right now. It's a pilot scale assessment of a GAC pretreatment with the StyDex. So I wanted to look and see if adding an activated carbon pretreatment improved the overall removal efficiency by any significant amount. So the thought here was that GAC would act as sort of a sacrificial column, since it's less expensive, to remove competing background constituents and get rid of some of those organic matters. And then the StyDex would be used to polish remaining compounds. And we looked at that next to an ion exchange resin. And what I saw is that the GAC pretreatment significantly increased overall contaminant removal. So you can see the orange line, that's showing the total removal in a previous pilot where we just had the one bed. And then the other lines are showing the total removal of all contaminants over the test with the 2-bed configuration. So the GAC significantly increased the removal, but adding GAC to a system isn't that expensive compared to using a specialty sorbent like StyDex or an ion exchange. Lastly, interestingly, this pretreatment increased the overall removal of short chain specifically, whereas the removal of longer chain like PFOA was sort of unchanged. So you can see on the right, that's the cumulative removal of PFOA across tests. And then over here, we're seeing the PFBA removal across tests. And we're actually getting PFBA removal when we use this dual configuration system. So getting rid of the competing background increased total available sites. And then we were able to remove those weaker sorbent compounds that are typically really difficult in adsorption. So overall conclusions is the StyDex outperformed activated carbon and ion exchange to remove contaminants from municipal wastewater. These beads were used in pilot tests over almost 4 months at an actual wastewater treatment plant. These beads were regenerable in a simple solvent and salt solution, desorbing most of the PFAS. And then when we used GAC as a pretreatment column, the overall removal was enhanced by about 4 times, with significantly better removal of weak compounds like PFBA and PFBS, which are the shortest chain. Well, actually, we didn't test PFBS, so I shouldn't say that, but in theory. So thank you to my lab members and Dr. Erin Packman, who is my advisor, and my funding sources, specifically, not a funding source, but special thanks to MWRD for allowing me to run my tests there. And then here's a picture of me with my pilot.
I think we have time for a question. Yeah.
So what's happening next with StyDex?
That's a good question. So the StyDex was developed in the Dichtel lab at Northwestern, so you would have to check what's happening with Will Dichtel.
I have a question.
But ideally, it would move to commercialization stages.
I have a question online. How would the flexible tubing of the peristaltic pump affects the results? Such tubing is expected to degrade with time and definitely will produce PFAS.
That's a good question. We do not use Teflon tubing. Our tubing is non-fluorinated. We also have done testing of all materials and any non-specific interactions with materials, and we do not have any adsorption to any materials or degradation. The entire pilot is fully non-fluorinated, so that shouldn't be an issue. And then I also do change out the peristaltic pump about once every 2 or 3 weeks because we get some biological growth in there, but not because of any sort of leaching. So, yes.
Did you test between the GAC and your, what's it called, StyDex?
Yes.
So tests in between that train?
Yeah. So we had sampling ports before the GAC, between the GAC and the StyDex, and then after that material. So we had 3 different sampling ports for each of the column sets. And then also testing within the tank to make sure what we're putting in is really what's being pumped out. Oh, from the GAC? Actually, I don't have them here. The GAC did a pretty good job, but I was switching out the GAC, so I really wish that I had done one where I just had GAC, that I wasn't switching. I actually was doing, I was changing out the columns for this first one on the furthest left, I was changing it out every 2,500 bed volumes, and then the second one every 5,000 to see if the change out frequency impacted performance. But over those 5,000 bed volumes, the GAC did better than I expected it would. And then we were quantifying the StyDex removal as how much was going into the StyDex from out of the GAC, so at that middle sampling point.
Okay, thank you, Emma.
Thank you.